This instructional video is designed to introduce you to the derivation of the Clausius-Clapeyron equation by taking advantage of some basic observations about the chemical potential. First, we want to look at is the idea that the chemical potential itself can be considered as a molar Gibbs energy. What this allows us to do is take results from the derivation of Maxwell relations and apply that in the following way. Because this is true, if we take partial derivatives with respect to pressure and temperature, then we'll get molar versions of those same quantities. So the pressure derivative becomes molar volume, and the temperature derivative is the negative molar entropy. At equilibrium, we assume that the chemical potential of one phase is equal to the chemical potential of the second phase. And as a result, we can write out total differentials for each phase and set them equal to each other. That means then that the phase 1 partial with respect to pressure times the straight differential plus the same for temperature has to also equal the same quantity for phase 2. And so at this point, it's now possible to make a number of substitutions and start grouping terms together. So we can have that the volume term here, dP minus S1 molar dt, has to be equal to molar volume for phase 2 dP and the negative of entropy for phase 2. So at this point, we use the same pressure and temperature because this process is equilibrium and our temperatures and pressures on both phases have to be the same. That allows us to group things together. So bringing this over here, we'll get V1 minus V2. Bringing this over here, we get S1 minus S2. So we'll have delta molar V dP equals delta molar S dt. At this point, we want to put differentials on the same side and deltas on the same side. So we end up with something that looks a lot like a proper derivative, dP dt, and a finite difference derivative here. But because this is an equilibrium process, it's possible to replace the molar entropy with the delta H for that particular phase change process divided by its temperature. And that gives us the Clausius-Clapeyron equation, that half of the Clausius-Clapeyron. So dP dt equals delta H T delta V. And that gives us the Clapeyron equation. So the Clapeyron half of the Clausius-Clapeyron is complete. But the challenge we have here is that because it's a finite difference derivative, there's a number of math reasons why that's bad, and what we really like to be able to do is guarantee that this quantity is not tiny, because then the terrible mathematical things won't happen. So as a result, we make the argument that if we're using something that involves changing into the gas phase, all of the volume is the result of the gas, and we know how to find a term for volume of a gas by using ideal gas law. So we have molar volume, then that's going to be equal to RT over P. This is on the bottom. So what we have next is we still have our derivative here. We still have the molar heat of vaporization over its temperature. And now we're going to have pressure over RT. Now we don't have to keep writing out delta pressure over RT because the change in volume here is due entirely to the gas volume, which means the pressure term is entirely gas pressure. Now what we have are a couple of constants. We have pressures and we have temperatures. So instead of keeping things as this derivative, we want to separate everything back out into two separate differential equations. This gives us dP over P, which we know we can integrate for our two pressures. And over here, we're going to pull all of our constants out. The heat of vaporization, which is a physical property, divided by R. And this becomes 1 over T squared dt. And so now once we integrate this, we'll have the Clausius-Clapeyron equation. We'll have both halves all together. So as a result, we get the natural log of P2 over P1 equals negative delta H molar vaporization over R. And we have 1 over T2 minus 1 over T1. And so as a result, what we find that we have is now the Clausius-Clapeyron equation right here. And what this lets us do is recognize that it is possible to determine something that's a fundamental physical property of a substance based on carefully designed measurements of pressures and temperatures. And it's all due to making a few clever observations about the chemical potential.